Good evening. I'm George Blumenthal. I'm the Chancellor at UC Santa Cruz. And thank you. And it is really my pleasure to welcome you here tonight to our Silicon Valley campus in the hub of innovation. Because Silicon Valley is where some of the world's great science advancements are happening. And we are a growing footprint in this region. Here, right here in this building through UC Santa Cruz Extension, which has about 17,000 students, through our new master's programs, and through programs that are soon to come. We will be soon have new professional master's programs here in serious games and in the human-computer interface. So stay tuned. This building is our new 100,000 square foot home. It's got terrific programs here. As I said, Extension is here. Games and Playable Media already is here in a partnership between computer engineering and the arts division at Santa Cruz. We have a master's program in electrical engineering, and as I indicated, more to come. So tonight is the beginning of a whole new venture, the Kraw Lecture Series. Our plan is to highlight a number of outstanding researchers in some of the great work of UC Santa Cruz scientists and technologists and humanists as well sometimes, to some of the people grappling with some of the biggest issues and biggest questions of our time. This is great for us to be able to display what we do, but I think it's also wonderful for the public. We will be having talks on subjects great and small, from the quest to find life on other planets, circling other stars, to work like our recent Breakthrough Prize winners' work. That's Harry Noller, who's made a number of discoveries about the ribosome, which are tiny cell structures that he calls the mothership of life. And Harry last fall won the 2016 Breakthrough Award for his lifetime achievement. So he will be here as well. We have a very close alum, however, who has really made this all possible through a generous gift to establish this lecture series. Attorney George Kraw and his wife Rafe really did this for us. And George is a history and Russian literature major from UC Santa Cruz class of 1971. And he has been a great friend of the university. And he's also been a friend of ours. His wife, Rafe, is also a great friend of the campus. George was recently the benefactor behind a project close to his heart, namely getting new portable field lights for the campus rugby squad. Now, George was actually on the very first UC Santa Cruz rugby team. And the lights that he gave us allows more practice time for the team as well as for other sports as well. But incidentally, George had another influence on us as well, because he showed great foresight even then, because that team members were among the first to call themselves the Banana Slugs. And that seems to have worked out for them. So this series was born out of George's belief we have a lot to brag about. His gift will allow us to showcase our faculty and highlight cutting-edge research taking place on our campus in Santa Cruz, as well as research taking place right here at this campus as well in the heart of Silicon Valley. We've already planned 3 future talks, and all of these will be free and open to the public. So I want to thank George Kraw and Rafe Kraw for their gift, and let me introduce and bring to the podium George Kraw.
Well, thank you, Chancellor, and thank you all for coming tonight. I'm very pleased that we've been able to put together this for this series of lectures showcasing science and technology at UC Santa Cruz. I myself am a child of the public education system in California, went to public schools, got a couple degrees from different UCs, and I recognize the great importance that our educational institution has played in the development of this state. Simply, California, as you may know, is the sixth largest economy in the world with only 40 million people. This achievement is in large part because of the great educational system we've developed and the discoveries that our researchers, our scientists have made. And UC Santa Cruz is an important part of this tradition today with its willingness to undertake the serious and difficult problems of science and research, but also to provide a path of social mobility for our students, for citizens of our state. In that regard, it's an investment in the human capital of the state. It is a small thing that Rafe and I have been able to do to help sponsor these lectures, and to my mind, an appreciation for all that it's done for me and my family. Tonight we're going to hear from Jonathon Fortney, who is a professor of astronomy and astrophysics and director of the Other Worlds Laboratory, which I have to say is one of the coolest names I've ever heard for any research institution. He received his Bachelor of Science from Iowa State in 1999 and his PhD in planetary sciences from the University of Arizona in 2004. Then from 2004 to 2007, he was a postdoctoral National Research Council Fellow and a Spitzer Fellow at NASA Ames. And he joined UC Santa Cruz in 2008. He continues to collaborate closely with NASA. He worked on the Kepler mission to find Earth-sized planets orbiting other stars. He's currently a member of the Cassini science team, which aims for a better understanding of Saturn, and he's a modeler and theorist, or is described as a modeler and theorist, who works closely with observers. The Other Worlds Laboratory is a new research institute at UC Santa Cruz and studies planets inside and outside the solar system. And this year, Jonathon is launching the Exoplanet Summer Program, ESP. As you may note, he has a way with acronyms, and it's an exoplanet ideas incubator that brings together researchers from all over the world to facilitate development of ideas in this area of study. So when Jonathon's not working on these very important issues, he's also has personal interest in being a runner, and he plays softball. So with that, I will introduce Professor Jonathon Fortney.
Everyone hear me okay? Yeah. All right. Well, it's a great pleasure to be here today. I'll note that Harry Noller and Harry's going to be the third speaker in this series, the Breakthrough Prize winner. He and I are on the same Santa Cruz City League softball team. So that's how I first got to know Harry last year. And only later did I learn, well, I should have known this earlier, what a phenomenal scientist he is. But I met him first as a softball player, second as one of my colleagues at UC Santa Cruz. So you can tell sometimes it's a little bit of a small town. So it's a great pleasure to be here. So I'll be talking tonight about finding and characterizing rocky planets or other stars. I'll focus a little bit more on this board over here because I'm closer, but I won't ignore the folks over here. I'll take you along as we move along. So there's my title. So how common is the Earth? So this really has two parts. One is how common are Earth-sized planets in our galaxy, but also how similar are these Earth-sized planets to Earth, right? Earth-like doesn't just mean Earth-size, it doesn't just mean Earth temperature. And we can start to answer the first half of that question, but we can answer the first half of that question, but the second half of that question is really a much harder question to answer. So we'll talk about that as we move along. The owl logo got mentioned before. It turned out really nice. That's all I can say about that. This was actually devised by a graduate student in Earth and Planetary Sciences. It was his first paid graphic design work, so it turned out great. So this map, this slide really, I think, conveys the imagery I want to bring home to you tonight. So this is a map of the quote New World in 1550. This was after about 50 years of exploration. People knew that there were these new continents. You could see the broad outlines. You could see that these lands were there. But still, we knew almost nothing about them. Right? If you think back to 1550, you can see the broad outlines. You can see South America. You can see North America. You had no idea what the extent was of North America. They were just guessing. And so the state we are in exoplanetary science today is that we know how common planets are around other stars. That's something that we never knew in the history of humankind until about, well, we started to learn this about 20 years ago. We only know this, I would say, for sure in the past 3 to 5 years. And so what we're moving towards today is going beyond just knowing the planets are there and trying to characterize what they're like. Just like hundreds of years ago, we were trying to move beyond knowing these continents were there. But it took many hundreds of years to learn what these continents were like. Did they have rivers? What were the people like in the interior? What sort of resources did they have? And so it's not exactly the same questions we're asking about exoplanets, but we'd like to know what they're like. We want to characterize them. So this is a thread that I'll come back to at the very end of the talk. I want to talk about how we know how common planets are and how we're driving towards learning more and more about them. So we'll start out simple. Planets come in different sizes, right? So we've got Jupiter and Saturn, Uranus and Neptune. Jupiter and Saturn are mostly hydrogen and helium. Jupiter's about 300 Earth masses. Saturn's about 100. Uranus and Neptune are about 15 Earth masses. And we have Earth and Venus, our twin planets. They're of course one Earth mass, right? So planets come in different sizes, and there's different types of objects. All these sizes are small, right? So to scale, we've got the Sun, we have Jupiter, we have the Earth right down there. So the Earth has a radius about 1/100th that of the Sun, and has a volume about 1/1,000,000th that of the Sun. And so this often makes trying to find planets very difficult, let alone learning anything about what they're like, what their atmospheres might be, what their composition is. And so the first way you might think about doing this is let's try to take a picture of a planet. Let's try to see what it's like. And you can do this, and people have worked on this quite hard over the past few decades, certainly in Santa Cruz as well as other places. But stars are bright, planets are not. So if you think about visible light, the light that we see and the light where the sun is brightest, the Earth is about 10 billion times fainter than the sun. So it's a tremendous technological challenge to see a very dim thing around a very, very bright thing very near to it. And so this is the best we can do with current technology. This is the Gemini Planet Imager, which was built at UC Santa Cruz. This is a very young, hot Jupiter-like planet that is about 100,000 times, 10 to the 5 times dimmer than its parent star. So this is 10 to the 5 times dimmer. This Earth is about 10 to the 10 times dimmer. So you know we have a ways to go, but it's through great technological feats that we're able to look at planets that are like this. So it requires, if you wanted to take a picture of an Earth like this, it requires telescopes that have not yet been built yet. But astronomers are they're very savvy, I would say. So sometimes you can use the star's light to your advantage, while a situation like this, the star's light is to your disadvantage. So you want to think of ways to find planets where you can use the star's light to help you rather than hinder you. And so one of these methods I'll spend a while talking about is the transit method, where you use the star's light. So if you see a planetary system that's almost exactly edge-on, if you monitor the brightness of that planet as a function of time, if a planet passes directly in front of its parent star, you'll block out a small fraction of that parent star's light. That's called a transit. And we can see that happen in our own solar system. From Earth, we can see Venus and Mercury pass in front of the sun occasionally. But we can see this for exoplanets as well. So we can use the star's light if the orientation is right. So Jupiter, if we imagine Jupiter passing in front of the sun, if we were an extrasolar system looking back at our system, Jupiter would block out about 1% of the sun's light during its transit. That's because Jupiter's radius is about 1/10 of the sun, so its cross-sectional area is about 100th. Earth is another 10 times smaller. So if you wanted to see an Earth transit, you'd have to be able to monitor the brightness of that star to 1 part in 10,000 to see that transit happening. If you wanted to see it happen over and over again, that transit would only happen once, of course, every year. So you have to monitor the brightness of that star to 1 part in 10,000 over the course of a year to see it happen again. But the nice thing about transits is that we can see them happen repeatedly, and the transit period, how long it takes to transit again and again and again, with Kepler's third law allows you to figure out the orbital distance, how far the planet is from its parent star. The closer in planets transit more frequently, the further out planets transit less frequently. So it's a nice example of using Kepler's laws to learn more about a planetary orbit. So this is Kepler over here on the upper left here. So in the early 1600s, Kepler used his 3 planetary laws of motion to, for the first time, predict when planets would pass directly in front of the sun. He was the first person to calculate that. And so he predicted when transits should occur. And in 1639, 9 years after his prediction, Crabtree in England was the first person to see a transit in the solar system. This is a painting of himself. Another great thing about this image is that you can see that astronomers over the centuries have really lost this amazing facial hair that Kepler was sporting. So I think we have a lot to live up to in terms of that as well. This is my favorite transiting planet image. This is the 2000. This has no science value at all. I just like this image a lot. This is Venus, the 2004 Venus transit. This is sunrise off of the east coast of Florida. And this is Venus passing directly in front of the sun at sunrise with a pelican and some fishermen. And I think it's just a stunning image of what we're trying to see in extrasolar planetary systems. But this is an example close to home. I remember seeing that when I was in grad school in 2004, and I've saved that image ever since. So we know that planets transit their parent star. The first extrasolar transiting planet happened in the year 1999, my second month in graduate school. And it profoundly changed the direction of my life and the things that I wanted to work on in graduate school. And even before then, Bill Barucki, who was a scientist at NASA Ames, thought about how we could answer this question of how common Earth-sized planets are around other stars. And he suggested that if we build a space telescope that looked in one patch of the sky and just stared at that patch for many years, if you were able to monitor the brightness of those stars, you would be able to see transiting planets, and you'd be able to answer this question. And so Bill, who retired a couple years back, in the mid-1980s, he wrote a paper about how you would be able to do this. And so they proposed this mission to NASA 4 different times every 2 years, and it was rejected. It was rejected, it was rejected, and finally it was chosen. And so each time it was, oh, this is a great idea, but we don't believe you can do this. And they gave them a little bit of money to prove they could do X. Then the next year, they got a little bit of money to prove they can do Y. And so in the end, they were selected as a mission. And so the basic idea was, if you sample a large enough number of stars, you can determine the fraction of sun-like stars that have Earth-sized planets in Earth-sized orbits. And so the whole key to the mission is that you have to have a large enough sample of stars. If you monitor 10 stars and you don't see any planets, that doesn't really tell you that planets are rare because you only sampled 10 stars. If you look at 100,000 stars and you don't see any planets, then you know planets are rare because you have a statistically significant sample size. And so the Kepler field, where the Kepler mission pointed for almost 4 years, it was picked to be just out of the plane of the Milky Way. If you sample in the plane, there's just too many stars. It's too crowded. If you sample too high out of the plane, there's not enough stars. So they picked a field of view that's right along here. And it's basically, Kepler is a very specialized space telescope. It's really like a 100 megapixel space camera built to do one thing and do it really well. Whereas the Hubble Space Telescope was built to look in the ultraviolet, in the infrared, and visible light, to take spectra, take images. Kepler was only built to do one thing, but to do it better than any other space telescope, and that's just monitor the brightness of stars over many years. And that's all it was designed to do. And so when you think about planets that potentially could be Earth-like or Earth-like orbits, that's where the concept of a habitable zone comes in. And so the habitable zone is this idea that there's a certain distance from a star where the planet's surface temperature might be adequate to have liquid water. On Earth, we think liquid water is essential to life. We don't know that that's true on other planetary systems. But if you want to find something that might be similar to Earth, you want to look for places that have liquid water. So the concept of the habitable zone is how close to your campfire do you need to be warm enough to have liquid water. So if you're around a more massive star, let's say twice the mass of the sun, you want to be further out because the star is brighter. If you're around a dimmer star, a dimmer red star, you want to be closer in because that's where the temperature is going to be right. And this depends on a lot of other things besides the temperature. You want to have the right surface pressure from your atmosphere. You want to have the right kind of atmosphere. So there's lots of details that go into this calculation. But the basic idea is something like this. You want to be in this habitable zone where we think liquid water could be. If you're too close, that water evaporates, it boils off. If you're too far away, that water just freezes into ice. So if we want to detect life that's similar to Earth, we might want to look at planets that have a temperature similar to Earth. And so the Kepler mission was optimized for finding these potential habitable planets. So let's call it something that's around the size of Earth. Let's say 75% to 50 to 1.5 times the size of the Earth, in things that are kind of like 1-year orbits. Earth orbits at 1 astronomical unit, 1 AU, so looking at things at 1 AU. And the Kepler mission monitored about 150,000 stars for 4 years, and it was a 1-meter telescope. Or I shouldn't say was, it still is, it's still operating. And so this is a person for scale. It's got solar panels all over the side. This is the top of the telescope that opens up. And so the feat of being able to monitor stars to a very high precision is really kind of amazing. And so this is, of course, the Transamerica Pyramid in downtown San Francisco. The equivalent is if you were staring at this fully lit up skyscraper, and you could see all the light from the skyscraper at once, if someone pulled the shade down about 10 centimeters, that is the change in brightness that you are seeing when a planet passes in front of its parent star. It's a tiny, tiny change. And you want not just see that, you want to see that repeat a year later. And you want to see it repeat a year later. So it's a tremendous technological achievement to be able to build something that has that stability to see that tiny change in brightness. And so this is one of my favorite Kepler systems. This is one I worked on a lot several years back. So in my research, I'm interested in planetary physics. What's the composition of planets? What are their atmospheres made of? What can we learn about them? And this was a really compelling system. This is Kepler 11. This is a system that has 6 transiting planets. 5 of them are interior to where Mercury's orbit would be around the sun. And all of the planets are more massive than the Earth. Okay? So this is a very massive, compact planetary system. And this is what the Kepler data looks like. So this is the brightness versus time. This is time in days. This is about 500 days. And so the raw Kepler data has all these bumps and wiggles to it, but if you take out the telescope heating up and cooling off and things like that, you can make this series over here. This is the brightness versus time. And this is 1.0000. This is 0.9995. These are very, very tiny changes in brightness. And so what you're seeing here is the fuzz of the planets. These are planets passing in front of the parent star for a few hours each time, a few hours, over the course of about 500 days. And it's color-coded here. So yellow is a planet that transits every 11 days. Red is a transit every 13 days. And so it's a closely packed system, and there's transits happening over and over and over and over again. And it's this rain, which is the detection of planets, that are periodic, the transits happening over and over and over again. Here's a cool triple transit where 3 planets are simultaneously passing in front of the star as we see it from Earth. And so this made the cover of Nature. This is the first really major discovery from the Kepler mission. 6 new worlds as posters up in my office because I think it turned out really cool. My graduate student Eric Lopez and I were able to show that this planetary system that we see it today is not the original planetary system. We were able to show that these planets are, because they're very close to their parent star, they're losing a lot of mass. All these planets are actually some ways similar to Uranus and Neptune. They have a thick hydrogen-helium atmosphere. But they're so close to their parent star that they're losing that hydrogen over time. They're evaporating. They're going from more massive planets to smaller planets as time goes on. And so what we were able to show in this system, and for the Kepler population as a whole, we're seeing remnant planetary systems of planets that used to be larger and more massive as time goes on. So this system really shook the field in that it had 5 planets, or 6, but 5 of them were all interior to Mercury's orbit. All were much more massive than the Earth. So where our planetary system has nothing, this planetary system has 5 planets, all more massive than we are. Most curiously, the parent star looks almost exactly like the Sun. It has no distinguishing characteristics to differentiate it from the Sun. It's what people call a solar twin. But yet its planetary system ended up nothing like our own. And I wouldn't say we have any good explanation for that yet. This whole concept of a lot of planets close to their parent star has really rocked our foundations of how we think planets form. So I've got a little movie here, which I think is fun, just to show the view. So we have some dimming events. If you look real closely, there's some transits happening over and over and over again. And we have the 6 transiting planets, 5 closer in, 1 a little bit further out. The 6th one is between Mercury and Venus's orbit. And there could be additional planets, right? There could be other planets in here that might be slightly misaligned, and we wouldn't actually see them transit, right? Because we need to see this system almost exactly edge on. So if you're misaligned by just a few degrees, you might be there, but we wouldn't see the transit. So that's an important thing to keep in mind when you look for transiting planets. You're probably missing a lot of the systems as well. So this is, it started already. We'll pause that. Okay. This is planetary detections over time. So this is the radius of a planet relative to the Earth. So Earth is here at 1, Neptune's 4 times the radius of the Earth, Jupiter's about 10 times the Earth's radius. These are different planetary detections. So we've got transiting planets in pink. In 1998, there were no transiting planets yet. This Doppler velocity, I'll talk about this a little bit later on. This is the method where you look at the wobble of the parent star towards or away from you and see the red shift and the blue shift of the parent star's light. Then we have some other methods I'm not really going to talk about, but we'll see the Kepler thing pop up in a minute. So we'll go back just to make sure we can start it up at the right time. So 1989, the first radial velocity detection, 1995, the second. And we can follow along. And this is when I started graduate school. There's the first transiting planet. It's called HD 209458b. It just rolls right off the tongue. Astronomers are horrible at naming things, but that's fine. As time goes on, we started to find more transiting planets. These transiting planets are much more likely to be found very close to the parent star, because we need to see the systems almost exactly edge on. So the closer a planet is to its star, the more likely it is to pass in front of its star. So it's a bias of the transiting planet method. And so at the time of 2009 was the time that Kepler launched. So I was picked to join the science team in 2008, and so I was at the Kepler launch in 2009. It was a night launch. It went up beautifully, and so we can start the clock over at 2009, and we can look at planets that were found not by Kepler over the next 4 years. So almost all these planets were found from the ground-based methods. People doing this radial velocity detections to find ground-based planets, more transiting planets. And you can gradually see that this diagram is getting more and more populated as we go to smaller and smaller planets, right? But in 2013, when people were trying to think about how common planets were, they were very focused on this region of the diagram here. And there were a lot of predictions that you'd form a lot of planets in here, but probably this region was, pretty devoid of planets. And it looked like, it looked kind of like that was true. But we can, on top of this plot, we can add what Kepler found. And so that's what Kepler found. So Kepler added almost 5,000 planets onto the census of 500. And what it showed without a doubt was that we were really only skimming the top of the whole sea of planets down below. So what you can see by eye is as you go to below about 4 Earth radii, there's a dramatic increase in the number of planets. And this is, of course, just actual raw detections. If you want to look at the frequency of planets, you have to figure out the geometric correction and the fact that these smaller planets are actually much harder to see in Kepler data. The bigger planets make bigger dips. Those are easier to see. And you can correct for all that in the Kepler pipeline that finds the planets. But it showed us that these smaller planets are dramatically more common than the larger planets, close to their parent star at least. You can see Earth is down here. Earth's in about a 365-day orbit at 1 Earth radius. The Kepler was designed to make it out to here, and you can see it didn't quite make it. And the reason why is that stars are actually noisier. Stars are more variable than we expected. The idea was that the sun is an average star. We'll base the whole mission on how noisy the sun is, how variable the sun is over time. But there was no way of knowing that the sun actually is not an average sun-like star. It's a bit quieter than the average sun-like star. So the main reason we weren't able to find these smallest planets in Earth-like orbits is that the average sun-like star is quite a bit more variable, and it's hard to pull out these very, very rare shallow transits. But there's a lot of data here, and you can surmise how common Earth-sized planets are, and I'll talk about that next. So Earth-like planets, I mentioned this before, how bright is your campfire, right? We want to think about this habitable zone. So if you're a hotter star, the green zone here, you want to be further away. If you're a cooler star, you want to be closer in. That's this concept of the habitable zone where you can have liquid water at the surface. So Kepler mostly focused on sun-like stars. So the sun is a G star, G over here. The sun is kind of a yellowish star. And astronomers classify stars. Astronomers are also really bad at classifying things. We classify things, and then the same classification scheme gets used 100 years later. So the big, bright, rare stars are the O stars. And so you might have heard in your life that the sun is an average star. You hear this all the time. That is just a flat-out lie. So the sun is average in that, okay, there's stars bigger than the sun, and there's stars smaller than the sun. So in that way, fine, it's average. But these little guys, these M stars, they're 75% of all stars in the sky. So nature makes the big stars very rarely, and nature makes the small stars much, much more commonly. And if you look at all the stars within 30 light years of the Earth, this is a plot from Todd Henry at Georgia State. These are all stars within 30 light years of the sun. This is the census. There are none of these big, bright objects, which is probably good because they tend to go supernova at a very short time, okay? Then we've got the A stars, the F stars, the Gs. These are the sun-like stars. Okay, there's about 20 nearby us. Go to the M stars, 246. So they're about 75% of all stars, these faint red stars. They're so faint and so red, a crazy thing is that there is not a single M star you can see with the naked eye. They're cool. They put out most of their flux in the infrared. And so you can't actually see them with your eye. They're that cool, but they're so abundant that if you put it on your infrared eyes, you see them everywhere. And so although Kepler wasn't able to do a great job of looking for planetary systems exactly like the Earth, these faint stars have much more close-in, potentially Earth-like planets. Their planetary systems are much smaller. Their habitable zone is much closer in. And Kepler did a great job of taking the census of these smaller objects in there. And so an example that you might have seen maybe 3 weeks ago now was a system called TRAPPIST-1. This is on the front page of the New York Times, the Washington Post, the Boston Globe. So this is Earth's system to scale. This is Mercury, Venus, Earth, and Mars. This system was not found by Kepler, although Kepler recently looked at this planetary system. And if you think about the TRAPPIST system, this has 7 planets around the size of the Earth. You got to zoom in. Can you see this little faint line here? So to scale, it's all in there. So this TRAPPIST-1 star is, the luminosity, the brightness of this star is 1,000th that of the sun. It's 1,000th as bright as our sun is. So if you want to be toasty by the campfire, you got to be really close in. And this system, through ways no one understands, I would say, has been able to make 7 around Earth-sized planets very close to the parent star. Of course, in our planetary system, we can draw images of the planets based on our knowledge of what they're like. In this planetary system, this is entirely due to an artist's imagination. And the thing I'm most interested in my career is being able to turn these artist conceptions into reality and trying to think about what these planets actually are like, what their atmospheres are like, what the planets are made of. And I think we're just now turning the corner towards being able to do that in other planetary systems. So with all the Kepler data analyzed, we can see that around 10% of Sun-like stars have an Earth-sized planet in the habitable zone. And that has kind of a large error bar on it because there's not a lot of detections, but that's probably not going to change by about a factor of 2. So around 10% of Sun-like stars have an Earth-sized planet in the habitable zone. But about half of all these faint M stars have an Earth-sized planet in the habitable zone, around half. M stars are 75% of all stars. About 100 billion total stars in the galaxy, 75 billion M stars. You add half of the 75 billion along with these guys, it's kind of unavoidable that we have about 35 billion, maybe plus or minus 5 billion, let's give it that, potentially habitable planets in our galaxy. These are Earth-sized planets in Earth-sized planets that receive the amount of light from their stars that's similar to what we receive from our sun. And so this is really mind-blowing in terms of thinking about the variety of planets that we might find around other stars. And it's a really huge phase space to search in. So what we want to think about as we move towards the next era of exoplanets is characterizing these planets. And so to characterize these planets, we really want to think about those that are nearest to the sun. Those that are nearest to us have the stars that are the brightest. They're the ones that we'll be able to characterize first. And so this next era of exoplanetary science that we're just starting in on is really focused on going beyond a census of planets, which Kepler delivered to us, to finding the nearest neighbors, because the nearest neighbors are the ones we can learn a lot more about. This is also the transit of Venus. This is transit of Venus as observed through a telescope that points at the sun continuously, a NASA telescope. And the part that interests me the most, and the stuff that I work on in my own research, is this here, right? So that is Venus's atmosphere lit up during the transit of Venus. In principle, if you could examine the starlight, let's say from the sun, or that is filtering through the planet's very thin outer atmosphere, if you could see absorption features due to molecules in the planet's atmosphere. In Venus, you'd see carbon dioxide. In the Earth, you'd see oxygen, ozone, some carbon dioxide, a little too much, methane. And so in my work, what I try to do is I make computer models of what the atmospheric composition and spectra of these atmospheres might be like to try to aid observers as they try to go out and observe these sorts of things. And then we work together to interpret what the observations mean. I should note that this very thin crescent was observed in the 1700s by a Russian astronomer named Lomonosov, who discovered the atmosphere of Venus from this effect with very rudimentary equipment, which is an amazing feat. So the James Webb Space Telescope will be launching in October 2018. And so the James Webb has a number of really intriguing science cases. Distant galaxies, how stars form. The thing I'm most interested in is how can we use it to characterize the atmospheres of planets. And people have tried to do this with the Hubble Space Telescope and other telescopes, but we've really been hindered by having to use telescopes that were never designed to look at these very small signals, right? So Hubble launched well before there were any transiting planets. And there's been upgrades to Hubble, but none of the upgrades to Hubble have really been specifically designed to look at exoplanet atmospheres. Whereas James Webb, a number of the instrument modes and a number of people on the science team are interested in this particular topic. So one of the things I've been working on over the past 2 years with Tom Green at NASA Ames Research Center is figuring out an observing strategy to use the James Webb Space Telescope to do the best possible observations of exoplanet atmospheres after it launches in 2018. It's expected that the telescope should last about 10 years, and we might be able to characterize the atmospheres of something like 100 planets, from gas giants to Neptunes, and probably a few potentially Earth-sized planets if they're around very nearby stars. The key of trying to characterize relatively small planets that might be like Earth is finding more nearby examples. We'd like to be able to look at transmission spectra. This is a very schematic figure, but for Earth, we'd like to be able to look for water vapor lines, oxygen lines. For Venus, we could see CO2 lines. For Mars, we could see CO2 lines. So in our own solar system, we have kind of two end member for rocky planet atmospheres. We have Mars and Venus that have mostly CO2 atmospheres. We have the Earth that has a nitrogen-oxygen atmosphere. So we have a really small sample size. If we learned anything from science, we should never generalize from a small sample size. It would be fantastic to have a much larger sample size of atmospheres to study. So we need to find more nearby planets. So NASA's next space mission is called TESS. So TESS is the Transiting Exoplanet Survey Satellite. And it differs a lot compared to Kepler. So Kepler stared at one patch of the sky for 4 years, and it never blinked. All it did was monitor the brightness of 150,000 stars for 4 years to find out how common planets are. The TESS mission, we already know how common planets are. Let's find all the nearby examples and clean house. That's what TESS is going to do. So TESS is going to launch in about a year, and it's going to survey different patches of the sky. So it has 4 separate telescopes. It's going to survey one patch for 27 days, another patch for 27 days, another patch for 27 days, and build up a sample around the northern hemisphere of its view and the southern hemisphere of its view. And then there's going to be overlapping strips. So in a lot of the field, it'll only be able to find planets on relatively short orbits. But that's fine, because these small planetary systems have transits that are pretty often. But in certain regions of the sky, it'll have continuous coverage for a year. And so the idea is to find a lot of these small planetary systems around the M stars, the planets that are potentially like Earth around these small, faint red stars, such that you can then follow them up with the James Webb Space Telescope. These things are designed to be operating at the same time. You find the planets, you characterize their atmospheres. And one of the things that we have in the University of California system, one of the things that we've devised and built in UC Santa Cruz is the automated planet finder. One of the things that's become really important for transiting planets is follow-up observations. I mentioned that if you see a transit, you know the size of the planet, its radius, and you know how often it transits. You don't know anything about the planet's mass. And one of the things we've been surprised of in exoplanets is the wide range of planets that can have similar sizes but different densities. If you want to follow something up that actually is potentially Earth-like, you want to find a rocky planet that has a high density. And so following up to get masses for planets is essential before we spend a lot of telescope time to characterize their atmospheres. So the automated planet finder is a purpose-built telescope that operates almost every night of the year, automated, looking at nearby bright stars in the sky, trying to find planets with this radial velocity method, this wobble method, where the planet and the star orbit around their common center of mass. You see a blue shift and a red shift of the parent star's light. It's especially useful for transiting planets, because we already know the orbit, we already know the planet's there. You can just follow up and get the planet's mass. Then you have the mass of the planet, the radius of the planet, and from the mass and radius, you get the planet's density. That really is essential in figuring out what planets you want to follow up. Because it's possible you could follow up a planet that you think might be Earth-like, but it turns out it's a very low density, and maybe it's more Neptune-like. That would be a really cool planet, but it's probably not what you want to go for if you want to find something that might be like Earth. And so in our department, we've been devising strategies, the best follow-up strategies for the TESS mission to get masses for interesting nearby transiting planets. But I want to turn in the last part of my talk towards kind of maybe the ultimate way of characterizing planetary atmospheres. So this is the Cassini view of Earth. So I'm also on the Cassini science team. Another topic I'm really interested in is Saturn's interior composition. The Cassini mission is going to dive into Saturn's atmosphere in September. That's the end of the mission. Right before then, we'll get once-in-a-lifetime data about the interior structure of Saturn. But this is a view of looking back at Earth. This is the modern version of the pale blue dot image, right? This is Earth right there. And again, one of the things that I work on in my scientific career is figuring out what Earth or other planets might look like in the light that they emit, in the light that they reflect, in the light that they transmit for transiting planets. And I mentioned before that this light for oh shoot, I'm going the wrong way. Sorry. This is a very small signal, right? This is a very small signal to see. And you don't know, perhaps, if the atmosphere is really, really thick with clouds. That might obscure our view of the molecules that we're trying to see in the atmosphere. So another way of thinking about these planets is not looking at the transmitted light, but maybe thinking about the reflected light. And that's historically how we've done a lot of work in our own solar system, is looking at reflected light and also looking at the thermal emission, the heat radiation from planets in our own solar system. And so the 30-meter telescope is a project that Santa Cruz is involved in, along with a number of the whole rest of the UC system, Caltech, other countries. And the idea is to build a much larger telescope than is available today. So the Keck telescopes in Hawaii have a 10-meter aperture. The 30-meter telescope, as the name implies, is 3 times larger across, 3 times the diameter, about 9 times the flux. And the thing that I'm the most interested in, and a lot of other folks in my departments, is the ability to potentially image an Earth-like planet and maybe do some basic characterization of the atmosphere during the era this telescope will be built, which is in the next 5 to 10 years. And so instead of thinking about reflected light, the thing we're most interested in is thinking about the heat radiation, the thermal emission of the planets. So this is the only kind of detailed graph I'm going to show you. This is the intensity from a star. This is a logarithmic scale. This is a star like the sun in red. And we have Jupiter, Venus, Earth, Mars down here. And so the Earth is about 10 to the 10 times fainter than the sun in visible light. So if you want to build a telescope to see an Earth-like planet around another star, around a sun-like star, it's quite challenging. If you go to longer wavelengths, though, the star gets much, much dimmer as you go to longer wavelengths, and the planets are still relatively bright. And so if you go to about 10 microns, long infrared radiation, this is still difficult, but a more readily solvable problem. The planets are only about 10 to the 7 times fainter than their parent star. If you think about what Earth looks like at around 10 microns, there's a lot of interesting features. This is a simulation that Andy Skemmer, who's a young professor in our department, ran, looking at Earth's spectrum. This is for an Earth-like planet around Alpha Centauri, as an example. And so we have in Earth's spectrum, we have water vapor, ozone, carbon dioxide, and these are integration times you would need with a 30-meter telescope to measure the brightness in these different bands. So it's a significant amount of telescope time, but it's an answerable question that you could do. You could build an instrument that would be able to measure the brightness of the planet in these different wavelengths and infer the abundance of things like water vapor, ozone, and carbon dioxide. This isn't something that's decades away. This is something that we really could do in the next decade to start this initial characterization of Earth-like planets around other stars. And so this is another nice diagram that shows this contrast. This is this 1 part in 10 to the 7 I talked about versus the angular separation, how far the planets are away from their star on the sky. Color-coded by this parent star. This is the small red stars. These are the sun-like stars. And the sweet spot for for this 30-meter telescope would be these faint red stars. And I already mentioned these faint red stars, half of them or more have an Earth-sized planet in the habitable zone. So that's really favorable in terms of being able to characterize these really common planetary systems, to be able to, if we can get down to planets around 10 to the 7 times fainter than their parent stars, we can start to characterize some of these planetary systems. So I just have a few more slides. So to me, what is amazing is that we're only just beginning to understand how planetary systems are built. The Kepler mission was a dramatic shock to our system for how we think planets are made and where they're made. The average planetary system has planets very close to their parent star where we don't have anything, and we're still trying to figure out why that is. There's really kind of unavoidable evidence that there's tens of billions of planets in the habitable zone in our galaxy. I mentioned about 35 billion, plus or minus 5 or 10 billion, but you're not going to move it beyond that needle. It's tens of billions of Earth-sized planets in the habitable zone. So our planetary system is in some ways a bit rare in that it's not the typical layout. One of the things I didn't mention in my talk is that we know gas giant planets like Jupiter are inherently not that common. Only about 10% of sun-like stars even have a gas giant that we can detect. So our layout seems to be a bit atypical. But at the same time, we know that our planet in some ways might be a bit common, and we know that Earth-sized planets really are common in our galaxy at Earth-like temperatures, mostly around these faint M-type parent stars. So the next stage really is to characterize the planets themselves, and that's the thing that I'm most interested in. I've been spending the past 10 years of my career trying to characterize the Jupiter-like planets and the Neptune-like planets, moving down to smaller and smaller sizes. And finally, with the James Webb Space Telescope and the 30-meter telescope, we can start to think about doing that same sort of characterization of the atmospheres for potentially Earth-like planets as well. And that's the work that I've specialized in at UC Santa Cruz. This will take some patience, but it really is the next era of exoplanets, and it really is coming at hand right now. So in the Other Worlds Laboratory at UC Santa Cruz, we really have a really unique expertise that crosses exoplanetary science, solar system science, planet formation, planetary atmospheres, instrumentation, how to build telescopes to find planets, how to characterize their atmospheres. So we work on formation of planets and planetary systems. We work on the evolution of Earth and Earth-like worlds. We characterize exoplanet atmospheres. That's one of the things I've worked on the most in my career. We use the automated planet finder to search for planets around nearby stars, those that we can follow up to actually image what they're like. And we're thinking hard about the science case and the design for instruments for the 30-meter telescope to move on to the characterization of Earth-sized planets. And so one of the things that was mentioned earlier is that this summer, for the first time, I'm leading a new summer institute that we hope to repeat year after year after year. I think about it as kind of like an idea incubator. So I'm inviting about 40 people to campus this summer for stays of 1 week to 4 weeks to bring their own groups, their own teams to Santa Cruz to work on what they feel are the most pressing problems for their research groups. And they're going to come interact with my group and the other groups in exoplanets here in Santa Cruz to kind of bring some of their ideas to reality, whether it's a new idea in planet formation or a new way to use the James Webb Space Telescope. I really want to make these owl summers kind of the place to be in exoplanets over the next few years, and I think we can really do that. So I want to come back to this map, because I think about this map a lot. So I hope I've convinced you the stage we're at is really this stage, right? We know how common planets are. They're everywhere. There's 35 billion Earth-sized planets that are potentially Earth-like in terms of their temperatures around other stars. We know that there's a map. We know this land is there. And we've done that relatively quickly, right? 20, 25 years ago, we didn't know of any exoplanets. And so it's going to be harder to characterize what the planets are like. It's going to take some time. Just like it took a lot of time and effort to characterize what these new lands were like, to send people there to explore them. But I think given the space telescopes we have and the ground-based telescopes we want to build, there's a very real chance that in our lifetimes we will know a tremendous more about rocky planets nearby the sun than we certainly do today. Thanks a lot.